Thank you very much. My talk today is related to this detection of gravitational waves that was made by LIGO more than 1 year ago. So it is motivated by this, but I will not be talking about any kind of experimental thing and any kind of new development in the realm of gravitational waves. What I would like to tell you today is I would like to recall an early history of gravitational waves. So my talk will end up in 1962. So that's the last moment. Will end in 1962. The main reason of this talk is just to recall the contribution of Professor Andrzej Trautmann to the theory. Yeah, okay. So let me start with the people which will be the heroes of my story. So you know this gentleman. Perhaps you don't know this gentleman. So there is Nathan Rosen, who will be also important figure in the story. Then there is Herman Bondi. You can figure out who is Herman Bondi because he's on both pictures. So that sorry. That's Herman Bondi here and here. I like these pictures because on these two pictures there are all three heads of relativity groups that were responsible for the revival of the theory of gravitational waves. There is Herman Bondi, the head of the group in King's College London. There is Peter Bergman, who was the head of the group in Syracuse. And there is Leopold Infeld, who was head of the group here in Warsaw. We have at least two members of this group at this time at this talk. There are Professors Ivo and Zofia Miłnicki-Pirula here. So they are coming from this guy. Okay. And my next hero is Felix Pirani, who plays something here. I don't know what kind of game is that. And next one is Ivor Robinson in his full glory. Typical Ivor Robinson. And the last one is, okay, so it's still Ivor Robinson. Here is Ivor Robinson with Bondi. Here is Ivor Robinson with Andrzej Trautmann. And Andrzej Trautmann is my last hero of my story. Perhaps those who know, they know that this is Andrzej Trautmann. The young people, this is Professor Andrzej Trautmann, okay? Here in particular is on a picture with his friend Subramanian Chandrasekhar. Okay, so these are the heroes of my story. And I should start from the basics, namely from prehistory, which is due to Albert Einstein. So Albert Einstein made his field equations in 1916, and they were highly nonlinear. So the first thing he did.
Yesterday I attended the conference and there was a talk about presentation. They told us to avoid, like orange on yellow or green on green.
That's green on green. Black on green.
It was deliberately hidden.
Yes. It was okay. It was not very hidden, but it was hidden, Okay, so that's the moral of the story, and that's what Einstein did. So here you have the first page of Einstein paper on gravitational waves from 1916. So it is. I learned just last week. I was thinking that was the first time that the word gravitational waves appeared, but last week I learned that the first time that gravitational waves appeared is 1905 in Poincaré's paper. It is Henri Poincaré who first was considering possibility of having gravitational waves well before 1916, in 1905. That's what he was saying. But as far as I knew, that's the first time that the word of plane gravitational waves appear in the literature. And what Einstein did, so Einstein linearized the field equation, so he just considered the metric as a Minkowski metric with some perturbation, and then he considered this perturbation to be small. And what he get the linearized Einstein equations for this trace corrected part of the perturbation, which looked like this. Here is the energy moment. Assuming some gauge conditions, that's true. Assuming that don't there conditions, that's true. So Einstein were able to put the equations for this perturbation like this, which outside the sources, where this is energy momentum tensor, was just a relativistic wave equation for the perturbation, and this justifies the claim that in the linearized Einstein theory, gravitational waves, which are perturbations of flat space-time metric traveling with speed of light, do exist. What Einstein did more even in this paper, there will be a story after, but let me first read this. So Einstein has also shown that in the linearized theory, his waves carry energy, and that the power of the gravitational radiation is proportional to the square of the third time derivative of the quadruple moment, as you see here. So he had also quadruple formula. The problem is that you can guess essentially this quadruple formula by dimensional analysis. You can guess that this should be proportional to the third time derivative squared of quadruple moment. The problem was how to get the coefficient, and Einstein made this coefficient wrong in this paper. So this coefficient was wrong, and actually Einstein's derivation was wrong. So he got a formula in this paper, but this formula was wrong. First, because of the coefficient. Second, there was genuine mistake in his calculations, and he was I think he realized this in 1918. He corrected this with a proper formula. So that's what Einstein did. And now let me say something. My talk has green lights and red lights, and immediately after this linearization, something which I call red lights for search for gravitational waves was switched on, and it was switched on by Albert Einstein, because he was aware of the fact that the presence of gravitational waves in the linearized theory does not imply that gravitational wave solutions are admitted by the fully nonlinear theory. So, of course, if the fully nonlinear theory admits gravitational waves as solutions, then one can use the waves from linear theory as approximation. But what if the fully nonlinear Einstein equations do not admit gravitational waves? If the nonlinear system doesn't admit such solutions, then, and Einstein believed that it is not obvious that they do. So then if they don't, then these plane waves from linear theory are just artifacts of linearization. Okay, so now these red lights, Einstein was worried about this all the time, and maybe I will summarize what one should do for overcome this problem. So you can divide this problem if fully nonlinear Einstein system admits gravitational wave. You can divide this problem onto sub-problems from the simplest to the most difficult. So let's start. So the first thing you can guess, I try to see if plane waves are admitted by the full theory. So that's the first thing. So I should define what is a plane wave if the full theory. So that's the first thing. If I define it, I can ask if such thing that I defined is a solution to the equations. And if I have a solution now, okay, if it is a wave, it should carry energy. So do such thing carries energy. And even I have these plane gravitational waves in the full theory, it doesn't solve the problem, because in the linear theory, if I have plane waves, I can just by superposition make any kind of wavefront. Here, there is no obvious way of superposing, and if I have plane waves which are unphysical sort of, because they are just in space-time from the beginning of the space-time to the end, they are not waves that are created. So I would like to have waves that are just created by bounded sources. So the next thing, so even if I solve the problem of plane wave, I would like to know what is not plane wave. And so the next step is what is the definition of a gravitational wave with non-planar front in the full theory. What is energy of such waves? Do there exist solutions to the full Einstein system satisfying this definition? And does the full theory admit solutions corresponding to the gravitational waves emitted by bounded sources? So I would divide this big question onto 7 sub-problems. And okay, so we as you remember, we were in 1916, and now nothing has happened for 20 years. The next story is 1937, and there's a paper of Einstein and Rosen, and I claim that this paper is about plane waves, although if you just read the first thing in the abstract, you will read the rigorous solution for cylindrical gravitational waves is given. So that's what is written here, and I claim that this paper is about plane waves. And actually this paper is about non-existence of plane waves, and this paper is about non-existence of gravitational waves at all. But there is this thing which just sort of contradicts to my words. But you can just look at the end of the paper. There is a note by Einstein added, and the note is, the second part of this paper was considerably altered by me after the departure of Mr. Rosen for Russia, since we had originally interpreted our formula results erroneously. I wish to thank my colleague, Professor Robertson, for his friendly assistance in the clarification of the original error. Okay, that's it. And then if you just look at this paper, it is published in some journal of Franklin Institute. Have you ever heard about such journal?
Yes.
You did? Who also heard about this journal? Okay, what?
It's a chemist.
Good, but yeah, so some people heard about the journal, but can you imagine that great Einstein sends his paper about gravitational waves first after 20 years to some Franklin journal? Yes. Okay, so let me elaborate about this story. This paper started by the letter of Einstein to Max Born, and look what Einstein writes to Max Born. Together with a young collaborator, I arrived at the interesting result that the gravitational waves do not exist, though they had been assumed as certainty to the first approximation. So he says that they do exist in linear theory, but I just, with my young collaborator, have proven that they do not exist. This shows that the nonlinear general relativistic field equation can tell us more, or rather limit us more than we have believed up to now. Okay? And this result that he's just reporting to Max Born was sent to Physical Review on 1st of June 1936 in a paper under the title Do Gravitational Wave Exist? And this was the paper with Rosen, and as you can see from the letter to Born, the Einstein answer to this question was no in this paper. So that was the thing, and
it was only 1 year after the famous, nowadays famous paper EPR.
I can elaborate after. This story is deeper and deeper. This story is deeper and deeper. But I have no time to tell you this. Okay, so let me go to the next thing. So I only concentrate on this paper for a while. So the paper was sent back to Einstein. So Einstein sent it by 1st of June. It was sent to Einstein by the editor of Physical Review, John Tate, on the 23rd July 1936, with 10 pages of review, 10 pages, you know. And Tate wrote to Einstein that he would be glad to have Einstein's reaction to the various comments and criticisms the referee has made. Look what Einstein had replied. What of Einstein had replied? We, Mr. Rosen and I, had sent you our manuscript for publication and had not authorized you to show it to specialists before it is printed. That was how this Tate dared to send it to any kind of referee, right? And then I see no reason to address the, in any case, erroneous comments of your anonymous expert, right? Okay, see?
I prefer to publish the paper as well.
Of course, in Franklin Journal, blah blah blah, right? Okay, so that's.
The referee was right because.
Okay, so who was the referee? Okay, maybe I just first I will just first tell you. Yes, I do. Yes, I do. So. So I just tell you what Einstein and Rosen did. They made an ansatz that they believed that will cover plane waves, and the ansatz was okay. Something there was two free functions of one variable, and then the Einstein equations reduced to a system of ODEs for these two unknowns. And analyzing these equations, they observed they even didn't find the solutions for these. They were simply making analysis like you just they behave like mathematicians, right? So they were just looking what are the properties of the equations, and they observed that the defining functions became singular at finite regions of space-time, and then they concluded that this is physically not acceptable, so plane waves are not transmitted by GR. Of course, their mistake was because this was before even the concept of manifold with coordinate patches penetrated the world of general relativity. So Einstein believed and Rosen believed that there should be a global coordinate system in which these plane waves have non-singular functions. But actually Einstein really believed that there is a global system. Then if you just take this solution and patch it properly, passing from one system to the other, you can interpret these solutions as cylindrical waves, which was told to Einstein by Robertson, right? So after, as I said, so Einstein just took this paper back in this Franklin Journal. He didn't change it much. He only changed the abstract and added this comment. All the other is, I believe, like in this paper submitted, although I don't know, because this submitted paper is not found so far. Okay, so that's the story. Who was the referee? So the story, the referee business was found out by Daniel Kennefic, who went to the archives of Physical Review, and there's a logbook. So look, this Einstein and Rosen paper, which came on 1st of June to the referee, to the editor. Then referee is Robertson, and it was sent of 6th of July to Robertson. 6th of July, and look, this Robertson was really great. On 19th of July, he sent it back to the journal with 10 pages referee report, right? And on 23rd, it was sent to the author, and then the author said that thank you very much, goodbye, right? So this was, and moreover, Kennefic went to the archives of Robertson, and he found several letters of Robertson to various people. There is a letter of Robertson to John Tate. Actually, there are two of them. I show you one of them. So this when Robertson writes 18th February. Remember, it was July, and it's now February 37, and that's what Robertson writes to Tate. You neglected to keep me informed on the paper submitted last summer by your most distinguished contributor, but I shall nevertheless let you in on the subsequent history. It was sent without even the correction of 1 or 2 numerical slips pointed out by your referee. So he says about himself, your referee, to another journal, and then it came back in gallery proofs, was completely revised because I had been able to convince him in the meantime that it proved the opposite of what he thought. You might be interested in looking up an article in the Journal of the Franklin Institute and comparing the conclusions reached with your referee's criticism. It's really very nicely written because he says about him sometimes I and sometimes about your referee. Okay? Okay, so that's the end of this story, okay? That's the end of the story. Maybe, no, maybe, I still have. So, nevertheless, that Robertson convinced them that what they have is just cylindrical waves, Einstein still believed that if there is a plane wave, there should be global system. And Einstein believed to the end of his life that plane waves don't exist. And moreover, he really believed that gravitational waves don't exist, which really stopped research on these subjects for another 20 years. So remember, 1916, 1937, and now we are in a gloom and doom period, that nothing has happened. And now we are coming to 20 years after, 1950s, mid of 1950s, and I start to revise my questions, my 7 questions. So what is the definition of plane gravitational?
The mathematical description of manifolds for those maps, which
It was already there, but even mathematicians, like these mathematicians in Princeton, like Eisenhower, was not using it.
but he kind of did it.
Who?
The differential geometry, so to speak.
I think that the notion of manifold was from 1920s really formalized. It really came from Riemann, sort of. Riemann had it, but it really didn't penetrate the for example, mathematics in USA was just bad at the time. There was nobody there before the Second World War, before Hitler came to power in 1933. There were no mathematicians in USA, and right.
How did they cope with this problem?
I am too young to answer this question, okay? Okay, so let me start with this. What is the plane wave in the full theory? Okay, so I can make my naive definition. Just to illustrate that there is a problem there, I just make a naive definition. So for me, okay, I am just an idiot, and I say, okay, a plane wave, what it could be? So a gravitational plane wave is a space-time described by a metric which in some coordinates t, x, y, z, where t is time-like, has metric functions only depending on t minus x. I put c equal 1. And preferably these functions should be sine or cosine, because in such a way there will be something like ripples of space-time will be moving with speed of lights in x direction with planar fronts. That would be what I would say. So let me just start with this. So I took a Minkowski metric and I added something. So since these terms only depends on t and minus x, they are oscillatory, they travel with speed of light, and not only because this red term, which is just a perturbation, this gamma in this Einstein linearization, and since it only depends on t minus x as function, so it does satisfy this box equation equals 0. So it is a solution of linearized equations, but actually it is even a solution of the full Einstein system. It is just Ricci flat. I calculated it is Ricci flat. So this should be a plane wave, right? So what was the problem? I had it in 5 minutes. Problem is that if I just make the transformation, coordinate transformation, I bring the metric to the flat Minkowski metric. So you see, it's not plane wave, it's just Minkowski metric. So my stupid definition is simply too naive. One has to define it in some different way. I didn't know. Okay, credit me for that. Okay, so now there is a first announcement in physics literature about existence of gravitational waves. So this is a Bondi's paper from 1957 in Nature, and it starts. The article starts as this: polarized plane gravitational waves were first discovered by Nathan Rosen, who, however, came to the conclusion that such waves could not exist because the metric would have to contain certain physical singularities. That's what Rosen, because it was really Rosen that came to Einstein with this example. Then they wrote paper together. Then Rosen wrote paper himself, and they simply didn't believe in this. And then, so that's the first quote. Now, the Bondi says further, it is therefore of interest to point out, as was first shown by Robinson, and has now been independently proved by me, that Rosen's argument is invalid and the true gravitational waves do in fact exist, Moreover, it is shown here that these waves carry energy, although it has not yet been possible to relate the intensity of the waves to the amount of energy carried. Okay, so that's what is written in Nature paper of Bondi of 1957. He claims that he has these plane waves in general relativity in full theory. And if you just look closer at this, so it is Bondi's paper from 1957, and Bondi is really considered as the father of this new theory of gravitational waves. He's really considered, like, if you ask a random person in USA that knows things, he would say that it's really Bondi. And then if you just look, and moreover, if you ask a random person in USA what was the turning point for understanding that gravitational waves exist and we should try to measure them, they always tell you, Americans at least, they always tell you that it was just Chapel Hill Conference in 1957, which was on January 1957. Here is May 1957, and here is Bondi, who is just the father of the theory. And look what Bondi says here. More recent work by Taub and McVitie showed that there were no unpolarized plane waves, and this result has tended to confirm the view that true plane gravitational waves do not exist in empty space in general relativity. Partly owing to this, Scheidegger and I have both expressed the opinion that there might be no energy-carrying gravitational waves at all in the theory. So that's what Bondi didn't believe in gravitational waves. And there is 5 here. 5 is various contributions to the discussions at the International Conference of Gravitation, Chapel Hill, 1957. So in January 1957, definitely Bondi didn't believe in gravitational waves. In May, he already believed, because it was shown by Robinson, and not him. It was Robinson who came to him with the solution, and then independently proved by me, right? So that's what I read here. By the way, there is also this story here. Robinson 6, and then Robinson Ivor to be published shortly. People who know Ivor Robinson, I happen to know him, they know that he never publishes anything. So to be published shortly, it means to be published never, unless he has friends who were Bondi and Pirani, and they put him on the paper after, which is precisely devoted to plane gravitational waves. And this is considered as a paper that really made a precise definition of gravitational waves. And let me give you this definition.
What is number 3?
Yes.
What is number 2?
I don't know. I know that these numbers, this series of articles has numbers, and I think that the last is 25 or something. Okay. How much time do I have? Half an hour. So I have to finish in 15 minutes because I want to show you a movie at the end of the story. So what is in this? What is this plane wave? So they were, at least it is not how Robinson get it, but it is how it is put in this paper of Bondi, Pirani, Robinson. So in Bondi, Pirani, Robinson, they are saying that we are very strongly motivated by analogy with plane waves in electromagnetism. And plane waves in electromagnetism, they have 5-dimensional group of symmetry. The Maxwell field has 5-dimensional group of symmetry. So they say, okay, so we just look for all solutions, Ricci-Flat solutions of Einstein equations that have 5 solutions, that have 5 symmetries, 5 Killing symmetries. And surprisingly, they looked at the list, which was at that time already available by Petrov, of solutions with large number of symmetries. 5 is large for me. And they found that there is only one class of solutions with 5-dimensional symmetries. And moreover, surprisingly, the group of symmetries is precisely the same group as in as a group. Is the same, is isomorphic to the group of symmetry of plane waves in Maxwell theory. And the solution is actually not one solution, but it's a class of solutions parameterized by one free function of complex function of one real variable, and real and imaginary part of this function can be interpreted therefore as a amplitude and polarization of the wave, and therefore can be modulated. So you can even put some information in the wave just by modulating this function f of u, right? And moreover, because they have a class of solutions, they were able to take this function in such a way that it can be interpreted as sandwich wave moving with speed of light, and they were looking for what this sandwich wave. So the sandwich wave, I mean, look, something like this. There is this function non-zero in some region, but otherwise it's just Minkowski space, and it's just moving, right? Because this U. They were putting test particles in this flat region, and they were looking what's going on with these test particles where they're heated by the wave, and they were seeing that these particles start to move. So they say, okay, so that the energy is transmitted from the wave to the particles because they start moving. Therefore, this wave do carry energy. So that's what they did. So if I just go to my problems, so the Bondi-Pirani-Robinson contribution solves the problem of what is the definition, that is a solution, and if they carry energy, yes. So they solved 3 out of my 7 problems. I have still 4, right? And all this fuss about plane waves would not appear if physicists would read mathematics literature, because actually the solution of this is actually much more general solution, something which is called PP wave, of which plane wave is only an example, because the solution for PP waves is just like, actually it is the wave that really Robinson get. Ivor Robinson get precisely this solution, but they only took the one that only depend on this real variable U. And this solution was obtained by Brinkmann in 1924, and although it was published in Mathematische Annalen, but it was even in English, so everybody could read this, but it was overlooked for years. Here is the solution, that there is a free function, a function m that should satisfy this equation. So it is actually he made it in any signature. It could be Riemannian, Lorentzian, or split signature. That's what, if you interpret this x and y correctly, as if y is a complex conjugate of x, that is precisely PP wave. Okay. So that was what Brinkmann did. So the next step is due to Felix Pirani. And it's very interesting. It's 1957, and he's the first guy that had an idea that the definition of a wave should be related to the properties of Riemann tensor. It's eventually. So Pirani had an idea that radiative solutions of the Einstein equations should be characterized by the properties of the curvature tensor, and he had an idea. He postulated that this radiative spacetime should be algebraically special. Whatever it means, it should have some, that the Riemann tensor should have some special algebraic properties at every point. That was his postulate. This algebraic speciality property is called Petrov classification of the Riemann, or of the Weil tensor. At Riemann and Weil, when Ricci is 0, is the same. So of the Riemann tensor, it is called Petrov classification. And at that time, actually Petrov did his classification wrong. He didn't get all the Petrov types. It was only definitely Penrose had it fully correct, the Petrov classification. So Pirani even didn't tell which kind of Petrov types of gravitational, which kind of special Petrov types should be assigned to gravitational wave, but he really said that it should be algebraically special everywhere. And this everywhere was something wrong, and this is the contribution of Andrzej starts to coming. So now I'm just going to Andrzej Trautmann. So this Petrov type. So what is this Petrov types? Roughly speaking, at every point of a Lorentzian for manifold, Weil tensor distinguishes 4 null directions. Roughly speaking, these are just eigenvectors for the Weil tensor. What, in some sense, because Weil tensor has a lot of indices, but if you just make it as a matrix, then you can have. Okay. Essentially, Weil tensor at every point distinguishes 4 null directions, and if it is very general, like you know, when you have eigenvalue problem, it depends on the matrix. If the matrix is special, there are multiplicities of eigenvalues and multiplicities of eigenvectors. So these vectors can coincide. So if a point of a spacetime, if a point of the spacetime, 4 different null directions are distinguished, that the such spacetime point is called algebraically general. If there are coincidences of these null directions, there is algebraically special. So it was not clear what Pirani means. He simply says that in radiative spacetime should have Weyl tensor at every point algebraically special, right?
These are not vectors, but antisymmetric tensors.
True, but because these are 2 forms, they define a null vector.
So he said they will not be generic, but they will be kind of degenerate.
Yes.
But he didn't point out which of those 4.
Because he even didn't know the classification, because Petrov made it wrong. Okay? So, but my next hero tells that actually Pirani was wrong, that it should be, that this algebraical speciality should be only asymptotic, and he says that it should be of this type, very far away. Okay? So let me just go.
Degenerated as possible.
Yes. So there is now these 2 papers of Andrzej Trautmann from 1958, which are part of his PhD thesis. So I don't know what you know about Trautmann, but 58, and Trautmann was born 33, so he was 25 years old when he was getting PhD, and is part of his PhD. The papers are.
Who's his advisor?
Leopold Infeld, formally, although Plebański. We will see it in a movie if I have time to show you the movie, okay? So these are 2 papers in which Trautmann solves my problems 4 and 5, okay? And
since you made a comment about the Franklin Institute journal, those papers were published
it is what
in a journal which, in some sense,
it is why
the word status was even lower.
yes, it is. But Trautmann was not Einstein at the time, you know. So and moreover, it is why I'm going all around the world telling about these 2 papers. It is why I'm just trying to advertise these papers everywhere. Okay. Okay. So. We can just skip it. I don't want it. Let's go. So Trautmann's idea was that from all, we are coming to the question: what is a gravitational wave in the full theory, in full generality, not plane? So his idea was that from all solutions of vacuum Einstein equations, selects only those that satisfy suitable boundary conditions at infinity. So he is a very different approach. Just look for boundary conditions at infinity. So Trautmann was engineer from Polytechnic, and he really knew any kind of radiation theory, and in particular he knew something which are called Sommerfeld radiation conditions for scalar field, which is a classical thing. You can just look in Courant and Hilbert. It is just there. And Trautmann just, when Plebański proposed him to look for gravitational waves, try to reformulate these Sommerfeld radiation conditions first to electrodynamics and then to any nonlinear field theory. So that's what he did. So in the first paper, he preparates for reformulation of the Sommerfeld radiation conditions for GR. He does it he just reformulates the Sommerfeld radiation conditions, and he looks how it goes in Maxwell theory, and he says that actually his radiation conditions precisely pick up these outgoing waves from the solutions of Maxwell equations. And the second paper does it for Einstein general relativity. So if you ask me what is a gravitational wave, or what is a space-time that contains radiation, the answer is very, very sort of boring. The answer is that there is such a space-time that admits a coordinate system, with some coordinate r that is affine parameter along geodesics escaping to infinity in such a way that the metric behaves like Minkowski metric and 1 over r modulo 1 over r terms. Moreover, the first derivative of the metric is just has 1 over r leading term with k being a null vector, and there is still a condition which is at first glance mysterious, but this condition is nothing but telling you that this coordinate system asymptotically should be harmonic, should be like satisfying the Donder condition, right? Far away. These are the conditions. So Trautmann said, okay, a space-time containing radiation provided that there exists a coordinate system in which the metric, its derivative, can satisfy this thing, okay, with some null vector, blah blah blah. That's what he says. And then he looks for the, okay, so he says, I have it and I will look for consequences of this. So consequences of this is, okay, so now I would like to define energy of this thing. And now that's a masterpiece that is totally overlooked by physicists. So Trautmann just tries to define energy of this radiative spacetime. So what he does, if you just look at Einstein equations, they have geometric part and they have this part which is related to the energy momentum tensor. But if you write this equation in terms of forms, you can see that this geometric part has something which is the total differential, and this total differential of this something is called Freud potential. So if you just rewrite this equation, you put this on the other side, then you can write these equations like total differential of something which is here is energy momentum tensor, and here is something. This comes from geometry, and this is just energy momentum of matter. And because here is total differential, that this quantity is conserved, therefore you can think about this as an energy of pure gravity. Right? So that's what Trautmann starts off. And now what he does, he just takes a space-like hypersurface. He doesn't say that this hypersurface is not, for example, asymptotically null. He says that in finite regions it's just space-like. And then attributed to such space-like hypersurface, he attributes for momentum, which is just integral of this t plus t, right? So he uses Stokes' theorem, goes to infinity, and he just expresses this integral in terms of spheres at infinity, right? So it is a global thing associated to a space-like hypersurface. That's what he does there. And then he proves that this thing is finite, provided that his boundary conditions are conserved. And moreover, he's just very meticulous. He just says, okay, there is no one coordinate system that my boundary conditions admit. So he just looks for all coordinate systems that are admitted by his boundary conditions, and he says that he shows that this quantity is independent on the choice of these coordinate systems that are adapted to a given boundary condition. So he really, and actually there's yet another discovery which is now called Bondi-Metzner group, BMS group, which is already in Trautmann's papers, again, 6 years before. So this BMS thing is in this, you were asking about these papers with gravitational waves number. So this BMS group is gravitational wave number, I think 19 or something, but Trautmann had it in his PhD thesis. And it's not called Trautmann's group, but BMS group. Okay, so then Trautmann shows that this quantity is independent on these transformations which are called BMS. And now he takes two hypersurfaces. He takes hypersurface like this, and next hypersurface, and then I should. No, I cannot because I am attached to. So he takes sigma 1 and sigma 2. He has this P of sigma 2 and P of sigma 1, right? So think that this is just asymptotically null, right? And then he associates P to this, and then he looks how much goes in here, right? So he just takes the difference. And again, using his condition, he's able to show that P0 part of this
Microphone.
Microphone. That P0 part of this difference is non-negative. That's what he's able to prove, that if his boundary conditions are satisfied, then he has this. I call it this weak proof of this, that this space-time carry energy, because he's unable to show that it's greater, strictly greater. He's just greater or equal, only able to show this. So, and for this proof, he strongly uses his boundary conditions. His boundary conditions guarantee this. Okay. So, moreover, he shows this. I should skip it. And in particular, he shows this. He shows that if his space-time satisfies the boundary conditions, that far away from the sources, it is algebraically special. So asymptotically, if he goes to infinity, the Riemann tensor is precisely of type n, as Pirani was mumbling in his intuitive understanding of things. I'm sorry. Yes, true. Pirani was a great man. I agree. So this solves my problems 4 and 5, and to really prove that these waves that he has carry energy, it would be interesting to have exact solutions that satisfies all the boundary conditions, and this P0 is greater than 0, right? And so these are this comment was about this energy carrying by gravitational waves, but still I have the other two things, and Trautmann answers all the 3 questions, including the one that I mentioned, in a paper with Ivor Robinson. So here is the contribution of Ivor Robinson and Andrzej Trautmann. And in a common paper, they find a class of exact solutions, which by construction can be interpreted as waves coming from bounded sources, because they have closed wave fronts. So that's what he did these are the waves. And then this equation, which is much more difficult to analyze than this one that Einstein and Rosen were analyzing, our superstar of geometric analysis in relativity, Piotr Hruściel, analyzed, and he shows that these equations have very nice properties, that, for example, they define this cry to which the wave escapes, and in particular, he's able to prove these solutions that there are such solutions that are radiating. The energy escapes to scry and eventually produces a horizon, and what you get at the end of the day is just a Schwarzschild call. So these solutions admit such a solution. It was proven by Hruściel in 1990. Okay, so let me just tell you what I believe that Trautmann's contribution to the story is very important. So it is first ever precise definition of a gravitational radiation in the full GR theory, first ever definition of energy of a gravitational radiation, first ever general proof that gravitational radiation carries energy, first explicit example of metrics describing gravitational radiation from bounded sources. That's what the Trautmann's paper was just submitted in April 1958, and to this Polish journal, and he went to King's College to give lectures about that, which was, as you say, May 58, June. So somehow he first sent the paper to publication, and then he was telling about this. Oh, for example, you see that the first 2 lectures were essentially the papers that I was just mentioning. So somehow these lectures were well received, and they were spread. So to summarize, that's my summary. And from 1962, all my green lights became red. Maybe it is not a coincidence that was the time that was the year. Maybe that Weber already said that he detected a gravitational. Okay, thank you very much. If you want to see a movie, I have a movie.
Yes.
Yes.
But it's another 13 minutes.